mechanics. Today we will study about the problem of particle in one-dimensional box. Consider a particle that is constant to move only in the x direction from x is equal to 0 to x is equal to L. Suppose this is the x direction, this is the x-axis, and a particle is moving in the x direction only. This is the boundaries of this box where x is equal to 0 and this is x is equal to L, and the particle is moving between these two boundaries and only along the x-axis. As the particle is moving inside this box, it cannot come outside this box, so the probability of finding the particle outside the box will be equal to 0. As the particle is inside the box, the potential energy inside the box will be equal to 0. While at the boundaries and outside the box, the potential energy will be infinitive. The Schrodinger wave equation in the operator form will be like this. It means h psi is equal to E psi, where h is the Hamiltonian operator in the x direction. And this Hamiltonian operator is given by this equation. H will be equal to minus h square upon 8 pi square m d square upon dx square plus v, where v is the potential energy and m is the mass and h is the Planck's constant. Now when we put this value in this equation takes the following form: minus h square upon 8 pi square m d square psi upon dx square plus v psi is equal to E psi. Now we will put this E psi in this side, and then this equation will take this form: minus h square upon 8 pi square m d square psi upon dx square plus v psi minus E psi will equal to 0. By solving this equation, we get this equation: h square upon 8 pi square m d square psi upon dx square E minus v psi is equal to 0. Now, if we multiply this equation throughout by the 8 pi square m upon h square, this equation will take the following form: d square psi upon dx square plus 8 pi square m upon h square E minus v psi is equal to 0. Now there are two conditions. One is outside the box and one is inside the box. So the first condition, if we take, when the particle is outside the box, then v will be equal to infinitive, as we have said earlier that the potential energy at the boundaries and outside the box will be infinitive. And if we put this value of v in this equation will take the following form: d square psi upon dx square plus 8 pi square m upon h square E minus infinitive psi is equal to 0. And this is possible only when psi is equal to 0. It means the probability of finding the particle outside the box is 0. It means the particle is not present outside the box. So we take the another condition, that is when particle is inside the box. And when the particle is inside the box, its potential energy will be equal to 0. It means v will be equal to 0. So we will put this value in the equation, and the equation will take the form: d square psi upon dx square plus 8 pi square m upon h square E minus 0 psi is equal to 0. So the equation will become d square psi upon dx square plus 8 pi square m upon h square E psi is equal to 0. Now we can replace this term with the k square for our easiness. This term will be replaced by k square. So k square will be equal to 2me upon h bar square. What is h bar? H bar is equal to h upon 2 pi. So we will put the value of k square here, and the equation will take the form: d square psi upon dx square plus k square psi is equal to 0. The wave function can be represented in the terms of the trigonometric functions, and the equation for this is like this: psi x is equal to a sin kx plus b cos kx, where a and b are the arbitrary constants. So that there are two conditions when x is equal to 0. This is at the boundary. So psi 0 will equal to 0 because the probability of finding the electron at the boundary is equal to 0. And when we put these value of x and psi in this equation will take the following form: 0 is equal to a sin 0 plus b cos 0. Now we know that the value of sin 0 is equal to 0 and the value of cos 0 is equal to 1. And when we put these value in this equation, we get the result that b is equal to 0. When x is equal to L, this is the boundary condition, and at the boundary the probability of finding the particle will be equal to 0. So psi L will be equal to 0. By putting these two values of x and psi in the former equation, we get this equation: 0 is equal to a sin kl plus 0. So a sin kl will become equal to 0 and sin kl will be 0. Then kl should be equal to n pi. This is the only condition when the value of sin will be equal to 0. Here n may be any integer, that is 1, 2, 3. So the value of n pi may be pi, it may be 2 pi, 3 pi, and so on. So when we put this value of kl here, we get kl is equal to n pi. So k will be equal to n pi upon L. But we know that k square is equal to 2me upon h bar square, and h is equal to h bar is equal to h upon 2 pi. So by combining these two equations, we get an equation like this, that is n square pi square upon L square. We have squared this equation because we get k square, and this will be equal to 2me upon h square into 4 pi square. We have put it here the value of h bar, that is h upon 2 pi. So we get h square up and 4 pi square. Now by solving this equation, we get E is equal to n square h square upon 8ml square. So this formula gives the energy of a particle in a one-dimensional box. In this formula, this n is the quantum number, that's value may be 1, 2, 3, 4. That is principal quantum number. H is the Planck's constant, m is the mass, and L is the length of the box. So from this equation, we can say that the energy of a particle in a one-dimensional box is quantized. It means it may be 1x, 4x, 9x, or 16x, or so on. For example, when n is equal to 1, the principal quantum number is 1, the electron is present in the first shell, then the energy will be h square upon 8ma square. When it is present in the second shell, the energy will be, here the n is 2, then n square will be 4. So energy will be 4h square upon 8ma square. Similarly, when the shell is 3, it means the quantum number is 3, n is 3, then E3 will be 9h square upon 8ma square. And similarly, when n is 4, then the energy will be 16h square upon 8ma square. As we have said earlier that the wave function psi x is equal to a sin kx because the another constant b has been become equal to 0. Now we can put the value of k, that is n pi upon L. So we get psi x is equal to a sin n pi upon L x. Now we know the probability of finding a particle in a small space between x and x plus dx is given by the square of the wave function. It means psi square x dx. As we know that the particle is found inside the box between the limits L and 0, and it cannot be found outside the box or at the boundary. So it will be definitely find inside the box. So the probability of finding the particle will be 1. Now we can integrate between limits L to 0. So we get integration between limits L to 0, psi square x dx will be equal to 1. When we put value of psi x from this equation into this, we get a square limits L to 0 sine square n pi x upon L dx is equal to 0. By integrating this equation, we can get the value of a, that is a constant, and it will be equal to under root 2 upon L. And we can put this value in the same equation and we will get psi x is equal to under root 2 upon L sine n pi x upon L. And this is a equation for the wave function in the particle in a one-dimensional box. Now the another important term is 0 point energy. What is 0 point energy? When the n is equal to 1, the energy is h square upon 8 ma square. This is the least or the minimum energy that an electron can have. It means electron is not at rest even at 0 degree Kelvin temperature. And this minimum energy is known as the 0 point energy. So this is all about the particle in a one-dimensional box problem. In our next video, we will study about the numericals and other questions related to the quantum mechanics that are asked in the exams. Thank you for watching this video. If you like, please subscribe, please share. If you want any more topic, you can send us. Thank you.